right, thank you, everyone. Thanks for being here. And these little toys, you can fiddle with them during the talk if you like. There'll be a part where you use them, and then at the end, you'll get to take one home. So feel free to interact with them. So I'm going to tell you about periodic trajectories on the regular pentagon. And here's the plan. So first of all, we'll talk about what are periodic trajectories. And then I'll talk about 3 things I really like about them, which I call buddies, families, and symmetry. And then at the end, I'll give a little plug for the Fab Lab and show you how these things were made. So the first thing is, what are periodic trajectories? So imagine that you have a standard billiard table, so like a pool table, rectangle, but with no pockets. We're not going to allow pockets because we want our ball to stay around. And we won't allow hitting the corner, because when you hit the corner, something unpredictable happens. So those are our rules. And our goal is to shoot the ball in such a way that it bounces around for a while and then comes back to where it started and repeats its path. That's the goal. Can you think of a way that we could do that on a standard pool table? Just go straight, yeah. So if you just shoot it straight across, then it will hit the side at a 90-degree angle and just bounce back and forth. So we would call this path periodic with period 2, because it has 2 bounces before it repeats. If you wanted to be more fancy, you could maybe start at that midpoint and then go down to the bottom midpoint and make a sort of a diamond pattern. Or if you want to be super fancy, you could do something like this. There are lots of options. OK, so this is a periodic billiard pass on a regular billiard table, but now the pentagon. So let's have a pentagon billiard table and have the same goal. We want to shoot the ball in such a way that it bounces around and then repeats its path. Can you imagine a way that we could do that? Yeah, same strategy. Same strategy. Let's start at one midpoint and shoot toward the other midpoint. Well, then we'll bounce so that the angle of incidence equals the angle of reflection. And by symmetry, sort of the same thing will happen. And then we just keep going and hitting the midpoints. And we get a periodic path of period 5 that looks like this nice star. Well, this is horizontal path if we start sort of down here at the bottom. But what if we started a sort of a horizontal path here at the top, like that? Well, then it would just angle of incidence equals the angle of reflection, go to this midpoint, and so on, and make this pentagon path. So this star and this pentagon path are examples that we'll come back to a lot in this talk. So just try to keep these in mind and have these be your friends when you think of a periodic trajectory on the regular pentagon. OK, so I want to talk about buddies. So this is joint work that I did with Lelièvre, who's a mathematician at Paris Sud, Université Paris Sud, just south of Paris, or Paris 11. And this is me and him in his office there. OK, so imagine, again, that we shot our ball horizontally. Now, this doesn't go right along the edge. It goes very close to the edge, but horizontally. Let's see what happens. So we bounce, 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 bounce. Oh, now we came back to where we started with period 10. Well, that is a really nice path. It makes this nice star. It sort of goes along the edges. What would have happened, I wonder, if instead of starting it here, we started our horizontal path just a little bit higher? Well, it's pretty similar. So the idea is you've decided, hey, I'm going to shoot my path horizontally. And now you're just trying different starting places and seeing what happens. So let's keep going. If we do all these different horizontal paths, we get different paths, but they're not really that different. Can you see that they're sort of fundamentally the same? They're just in a slightly different place. So if we push our starting point all the way up, all these paths are basically the same, but something's about to happen. We're about to slide across a vertex. So something different is going to happen. Ready? Yep. OK, now this path looks very similar. There's still this big star. But you'll notice that instead of sort of skirting along the edges, now we just make this very small jump across the corner. So this path is different. And if we keep pushing our path up, you'll see that we get this regular pentagon path instead of this star. Pretty neat, right? And if we keep pushing it all the way to the top, we sort of get back to where we started. So here's some things to notice about these kind of paths. First is that the red and the blue trajectories hit the edges in different orders. So not only do they sort of look different, but they're kind of fundamentally different things. Then on the other hand, here's some things that are the same. So all the red trajectories are the same length as each other. All the blue trajectories are the same length as each other. And it turns out that the red trajectories are longer. They're the golden ratio times the length of the blue trajectories. And I'll talk about what that is. So that's where we're going. So these are some things we can talk about buddies. So first, let's talk about the order. So the red trajectory, if you look at it, it actually skips an edge every time. So if we start it on this left edge, we go over to that right edge, and we totally skip the bottom. And if you keep track of where it goes, well, then it sort of goes across again, and each time it skips one edge. It never goes to the very next edge. On the other hand, the blue hits the edges in order. It starts at the top left edge, then goes to the top right edge, and it just keeps hitting them just in a nice circular order. So they're fundamentally different. That's one way we could differentiate between them. Now, all the red trajectories are the same length. The way I like to think about this is that the pentagon is sort of like a wire. Imagine that the pentagon is a wire frame. And the red trajectory is like a ribbon that you've wrapped around it. And then if we go from this path to the next one, you're just sort of sliding the ribbon up and then adjusting everything. And everything just slides up nicely. So all of these, the ribbons are all the same length. But then when we flip to the blue trajectory, it's a different length. You can see maybe that there's less ribbon on the page. There's just less here. But all of these are also the same length. So we could slide our blue ribbon as well. Yeah?
So that implies that when you're going from the one pattern to the other, going through that vertex,
Yeah.
there's a discontinuity in the length of the ribbon.
Yeah, you just couldn't do it. If you tried to slide your ribbon across that vertex and make everything happen, it would be too short.
Even though it's just an infinitesimal change in...
Yeah, so when you slide across a vertex, things go wrong. Yeah. It's a discontinuity in the system. Everything is continuous. It's going a different direction. Yeah. So these guys are all the same length. And now the red length of the red ribbon is the golden ratio times the length of the blue ribbon. And one way to see that is to draw them on the same picture. You can see that there are 5 pieces to the red trajectory in this picture. There are 5 pieces to the blue trajectory. And in each case, like this red one is longer than the corresponding parallel blue one. So you can see that the red one is longer. OK. Now, the golden ratio is this number that has been admired since antiquity. People think that this ratio, this golden ratio, is a beautiful ratio. So in mathematical terms, it's about 1.6. There's an expression for it. And here's some of the places it has come up. So for example, here is the Parthenon. And the idea is that the ratio of its width to its height is this same ratio, this 1.618 to 1, the same as our red ribbon to blue ribbon length ratio. It's also rumored to be the ratio of various lengths in your body, such as the length of your belly button to the floor versus your belly button to the top of your head is apparently in this ratio. Your hand is apparently in this ratio. Your head is apparently in this ratio. Your credit card, your pieces of paper, human beings like this ratio. For us, the reason it comes up in pentagons is because if you draw the diagonal of a pentagon, it is exactly the golden ratio times as long as the edge. So that's where it comes up for us. So there you go. So back to buddies. So I consider all the blue trajectories to be basically the same. I don't differentiate between them. They're all the blue trajectory, even if it's shifted over a little bit. And I consider all the red trajectories to also be the same as each other. But I consider the blue and red to be each other's buddy. Because it's basically like you made a decision, I'm going to hit my ball in this direction, and then depending on where you put down your ball, you get either the red or the blue. So they're buddies. They're intimately related. So, for example, here's a pair of some buddies. This is the one that we've seen. So we have the long buddy on the left and the blue buddy on the right. And there they are together. And you can see that they have parallel parts. You can see that pretty clearly when they're put together. Those are parallel, all the bits are parallel. Here's another example. This one's more complicated. So these are buddies. You can always know that the red buddy has 1.6 times as much stuff as the blue buddy, because the ribbon is longer. But when you see it, you can see that there are parallel bits in this picture as well. Can you see that there are a lot of parallel things? OK, so they're parallel buddies. Here's some other examples. Aren't they beautiful? Aren't periodic billiard trajectories so beautiful? Check it out. Look how nice those are. They're so nice. This one, you might not think that these are buddies, because as these look kind of different, but they do have these sort of spikes. They both have these sort of spikes, so you can tell that they're related. They have a family resemblance. And so on. Now, there are some asymmetrical trajectories. So these are ones where they don't have the rotational symmetry that we've seen everywhere. But again, they each have a buddy. And it turns out that if one of the buddies doesn't have the rotational symmetry, if it's asymmetrical, the other buddy, like both buddies, are going to be asymmetrical. So here's another example of that. We have these two asymmetrical buddies. that are parallel bits. Okay, so they have, as you can see, these parallel bits as well. So how about for you? So on the table here, you have 8 trajectories, and I want you to match them into 4 pairs of parallel buddies. Go. Okay, so maybe that's enough. Thanks, guys. I'm so excited that you're so excited about this. Okay. So, great. So maybe the first thing to do is ask who's paired with this guy? Yeah, this one. Exactly. Yeah, these guys are paired together because they both don't have the symmetry. Nice. Great job. Okay. How about this one? Can you say who's paired with this one? Yeah, the one on the other side. Yeah, exactly. They both have these sort of stars in the middle. Nice. Okay, how about this one? Who's paired with this guy? Yeah, the one at the top. Yep, the one at the top is paired with this one. Good. Okay. And then the last 2. And then these 2 are paired. So it goes like that. Okay. Okay. So should you forget these answers, the answers are actually on the back. Not there. So on the back of each little plastic piece, it says a periodic path on the pentagon from Diana Davis, 2018, and then there's some number, and then it says either long or short. So if you match the numbers and the long and the short. Yes, the answers are on the back. So take your favorite and take them home. Okay. Okay, hey, there are a few more things I want to tell you about these, so I'm going to do that. So families, so if you saw the video looping at the beginning, you saw some families. This is joint work with Barak Weiss. We were just working on this just after Christmas in January. So in order to do this, I'm going to use the double pentagon surface. So we're going to use this trajectory on the surface. But first I'll tell you what the double pentagon surface is. So here's a bit from my Dance Your PhD video. So Libby here is demonstrating what it means to walk around on the double pentagon surface. So it's a surface because every edge is glued to the parallel edge. So here when you put your arm across the yellow, you end up with your arm across the other yellow. So it's a surface just like the surface of the Earth is a surface. No matter where you go, you never fall off. So that's the idea. And we're going to use the surface because periodic directions, like ways that you could walk on this surface and come back to where you start, are the same as the periodic directions on the pentagonal billiard table. So, good. So here's a trajectory on the double pentagon surface. If you started here and walked, you would get back to where you started. And you can see it has these 4 parts, 1, 2, 3, and 4. Instead of drawing all these on the same picture, I'll just draw it on this one picture where they each get their own pentagon. And now in order to turn this into a billiard trajectory, I have to fold it up. So I'm going to fold this one onto there, and then fold this one, and then fold this one. And what this gives me is a billiard trajectory. The way that we did it, the angle of incidence is equal to the angle of reflection at every bounce. So this is a billiard trajectory. But of course, if you hit your ball like this, it wouldn't stop there. It would keep going. In fact, it would repeat the same thing. So this gives us a whole billiard trajectory. So we just have to do it 5 times. So this is the plan. We're going to start with a trajectory on the double pentagon surface, and we're going to twist it. The way you can imagine this is if you made a bagel out of dough, and then you just twisted it over and over and over and over and over again, you can imagine it would get some sort of twist lines on it. That's what we're about to do. Ready? Here we go. Twist, 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 twist. This is what happens to our trajectory when you twist it over and over and over and over and over again. Okay, and so on. Okay, now we're going to take each of these guys and fold it up into a trajectory on the pentagon to get a billiard trajectory. Ready? Okay, so here's the first one. This is the one that I made by doing it once and then doing it 5 times. And here we go. Ready? Aren't those beautiful? So beautiful. How could we not study these? They're so beautiful. So here we get pentagon billiard trajectories. Okay, the last thing I'd like to talk about is symmetry, which I talked about a little bit. Some of the paths have rotational symmetry and some of them don't. This is again joint with Lelièvre. This is a are us doing something more fun than sitting in his office. This is us sailing in Boston this past summer. So as you recall, if you start with something on the surface, you fold it up to get a path. And in this case, we get an incomplete billiard trajectory. To get the whole thing, we had to do 5 of them. But some paths aren't like that. So for example, here's a different path on the surface. You can see it starts sort of low on the left edge, and it ends sort of low on the left edge. So it's this periodic. And when we fold this guy up, we get a complete billiard trajectory. Now this looks like only 2 pieces, but you saw it created, so you know what it is you shot your ball here. It was perpendicular, so it bounced right back. Angle of incidence equals the angle of reflection. It bounced up here perpendicular, bounced right back. So this is just 4 bounces. Isn't that a cool path? We never even thought of that path before we had the computer tell us what all the paths were. But here it is. So the idea is that some paths need 5 copies to complete, and those are the ones with symmetry. And some paths don't. They're complete after you fold them up, and those are the ones that do have symmetry. Now, I'm a little biased toward the paths with symmetry because I think they're very beautiful. For instance, that whole family that I just showed you, such a beautiful family of symmetric paths. But I'll just show you some of the asymmetrical paths. Ready? So here's a little family gathering, family gallery. I think that if you ask someone what their favorite is, so like you each picked one already to take home, it's sort of like a Rorschach test. It says something about your psychology. There's something to be said about the people who like the asymmetric paths the best. This is the one that you have. It's sort of nice, right? How about somebody, what would you think about somebody whose favorite was this, huh? Okay. So the last thing I'd like to tell you is how I made these things. I made them in Swarthmore's Fab Lab. They call it the makerspace, but I think it should be rebranded as the Fab Lab because Fab means fabrication laboratory, and the person that coined this term, that made the first Fab Lab at MIT, is a Swarthmore alum. So we should embrace this, Fab Lab. So here's the idea. This is the Fab Lab. It's got a laser cutter here, which is a very big machine that is very expensive. Then it's got a computer, which you can use to run this machine. So this is, I think, about $40,000. And then it's got these 2 3D printers. 3D printers are much cheaper. They're in the range of a couple $100s. And this runs all the time. And there's also a separate maker space where you can use tools and stuff. So I made these things on the laser cutter. It's quite easy. You make a file. You say file print. It prints it. You can do anything. You can do a Microsoft Word file. The key is to make a good file. So 3 steps to make these pentagons. First, I engrave the trajectory. Then I flip them over. And then I engrave the back. So I have videos of this happening. Is it going? No. Try again. There it goes. Pretty neat, huh? So this is called vector engraving because the laser actually moves in the direction of your thing. Okay, and then next, this is a little bit later. I had to do them twice because they weren't so great the first time. So this is the whole sheet of them all together. So I printed them out, and it took a couple of hours. Then the next thing is I had it cut them out. And then the next thing is that I flipped them over by hand. So here's the whole sheet. It cut them all out, and I went and I individually flipped each one of them over. And then to do the engraving on the back, that's called rastering because it doesn't move in the exact order of what you want. It just sort of moves like a typewriter or like a printer. It just prints one line at a time. So that's the idea, and that's how we got the engraving on the back that says, a periodic path on the Pentagon from Diana Davis 2018. So, thank you very much. Yeah, question, Paul?
Am I right that the asymmetric ones are handed, at least if you assume you can't?
The asymmetric ones have bilateral mirror symmetry.
Yeah.
So actually,
The left and the right
there isn't. They're symmetric across an axis, so they actually aren't handed. Yep. Yeah, good question. Yeah.
This may be a dumb question, but why is this interesting besides that it's cool?
Yeah, why is it interesting? So it's mostly that it's cool. You can find applications to chemistry, like that there are atoms bouncing around in rooms and stuff, and so this is sort of like that. You can have applications to physics. So if you have 2 point masses bouncing back and forth on an interval, it can be exactly translated into a problem about billiards on a triangle. But mostly it's because it's beautiful and interesting. And there's so much rich mathematics. Billiards is actually very hot right now. The last 2, there are 4 Fields medals awarded every 4 years, and 2 of them in the last cycle were to people doing generalizations of billiards. So it's very, very exciting and a very rich field. Yeah. Yeah.
How old is this branch of mathematics?
So billiards, people were thinking about billiards on the square in the late 1800s. It's related to continued fractions, which was from earlier, but there's been a recent explosion, actually, quite recently. So all the stuff that I did today about the pentagon started in like 2010. And the stuff about the families is like less than a month old. It's very exciting. Yeah, Jack?
This is a very broad question. If you could summarize how much of this translates to other shapes. I'm assuming regular polygons.
Yeah, regular
How
polygons.
much of what you talked about here translates to those other spaces, and how much of this is pentagon specific?
So it's basically pentagon specific. Here's something amazing, okay? People understand what the periodic trajectories look like on the square and rectangles. People understand that. They've understood it since the 1800s. They don't understand for any other shape except the pentagon because we just did it. That's it. So it's most likely the same techniques would generalize to other regular polygons like regular heptagon, regular hexagon, stuff like that. You would just have to do it. And it probably wouldn't be quite as elegant as it is for the pentagon because the golden ratio makes things come out well. Probably the same kind of thing would happen, but nobody knows. And for non-special polygons, very little is known actually in billiards. There are many open questions. Yeah. Yeah.
I recommend an art application. Find a pentagon-shaped ceiling and do a colored mosaic.
It would be beautiful, right? Especially for the, so as you can see, I'm wearing the jewelry. So I have this pentagon here. I have pentagons on my ears, and then I also have this shirt. But if you could imagine one of these, like maybe coloring each of the spaces a different color, it would be very beautiful, right? Yeah, question?
So are you generalizing this to like n dimensions and that?
So 2 dimensions is already very interesting and sort of complicated and hard. So 3 dimensions for sure would be interesting. People ask about other shapes. People ask about more dimensions. People ask about hyperbolic space, about spherical things. I have no idea. But it's all very interesting. Good question. Yeah.
Depending on the source of the golden triangle back when, in other words, the discovery of that ratio, a regular pentagon.
Oh, right. Oh, is the regular pentagon where it comes from? So where the golden ratio comes from is, I'll just bring up the picture of the Parthenon. It will be easier that way. So the golden rectangle is it's the rectangle where if you cut off a square, the remaining rectangle is in the same proportions as the original. And if you just write down that equation and you solve it, you get 1.618. And somehow this was seen to be the most symmetric kind of a rectangle that you could have.
Turns out the pentagon has the same.
And it turns out it comes in the pentagon too. Yeah, sometimes these things that are beautiful, they end up coming up a lot. So it comes up in spirals of flowers, gosh, and all sorts of things. Yeah, the Fibonacci sequence, rabbits, comes up, when things come up, they come up all over. Yeah, thank you. All right, thanks guys, thank you very much.